Hi, this is Tzvi Rosen with another lecture in our online course on matrix theory. Today we'll be talking about special matrices, specifically triangular matrices, diagonal matrices, and symmetric matrices. And this corresponds to section 1.7 in Anton and Ruris. Start with diagonal matrices. The idea of diagonal matrices is that our matrices A have entries ij, which are always equal to 0 unless I is equal to j. Visually, what this looks like is you have non-zero entries on this main diagonal. But then everywhere else is 0. Zeros here, zeros here, up here, down here, lots of zeros. So really, the only entries we're interested in are these n entries on the diagonal. Okay, so A11, A22, ANN are allowed to be non-zero. Okay, that being said, they don't have to be non-zero. A matrix that includes some zero entries on the diagonal will also still be called diagonal, as long as everything off the diagonal is 0. Sometimes we'll write this more like this, with 1, let's say 2, etc. And then instead of writing out a lot of zeros, I might just put a big 0 here, a big 0 here, or I might omit them altogether. So it would look like that. Okay. So looking at a diagonal matrix, how can we determine whether or not it's invertible? So let's recall that a matrix has an inverse, means that we have a matrix, there is a matrix A inverse satisfying A inverse equals A inverse A equals the identity matrix of size n by n, assuming that A is an n by n matrix. Okay, well, when will this happen? So let's say our diagonal matrix A has entries A1 through AN on the diagonal. And we want to know what the inverse would look like. So let's say it has entries B11 through BN1. Sorry, this should be B1N. BN1, BNN. So the first thing we'll see is that this matrix should be diagonal. Okay, so this is our A inverse. Needs to be diagonal. This product has to be equal to the diagonal matrix, which is just 1s on the diagonal. In other words, the identity matrix. So how do we know that the inverse needs to be diagonal? Well, suppose we have some off diagonal entry which is non-zero. For instance, B12. So we're going to suppose that B12 is not equal to 0. Okay, well, then if I'm looking at the dot product of the first row with the second column, What that tells me is, so row 1 of A dotted with the second column of the inverse, that's going to be equal to A1 times B1, too. But we know this is supposed to be 0 based on the entry here, right? This is supposed to correspond to first row, second column. So this tells us that A1 would have to be 0. But then if A1 is 0, then the product of the first row with the first column will be A1, B1, 1. And if A1 is 0, this also has to be equal to 0. But we know it's supposed to be equal to 1. So that means that it's impossible for B1, 2 to be non-zero. Must be 0. Otherwise, we would find ourselves in one of these weird contradictions. Okay? And that tells us the same argument works for any off-diagonal entry. So it must be the case that that the inverse matrix, A inverse, must also be diagonal. Okay. So given that it's diagonal, what will its entries be? Well, if this is A1 through AN, and then our inverse matrix looks like B1 through BN, and we want this to come out to 1 through 1, well, what does this correspond to? What do the entries of the product look like? They're going to look like A1, B1, A2, B2, etc., down to AN, BN is equal to 1 down to 1. Okay? So the product of these two diagonal matrices will be the identity matrix if we set BI to be equal to 1 over AI. Okay, but this only makes sense if all of the AIs are non-zero. Otherwise, you can't divide by them. If you have an AI which is equal to 0, you can't divide by it. So that tells us that a diagonal matrix is invertible only if all diagonal entries are not equal to 0. Okay. And this is actually if and only if. Okay. So if you look at all of those entries and they're non-zero on the diagonal, then you can confirm that the matrix is invertible. Okay, and so what do they look like? Well, the inverse we've just seen is, so if assuming that A is equal to A1 through AN, then A inverse is going to be 1 over A1 through 1 over AN. You could also write this as the minus 1 power. Okay? A1 to the minus 1 down to AN to the minus 1. Okay? How about powers of the matrix? Well, based on how we saw these diagonal matrices multiply, whenever you take a power, so let's say the square, all you're going to end up doing is squaring all of the diagonal entries. Okay, and this is true for an arbitrary power. Okay, so if you replace this with k. This will be a1 to the k up to an to the k. And the same is true for the inverse matrix. If you want to take negative powers, a to the minus k is equal to a1 to the minus k down to an to the minus k. Okay, maybe we'll do a concrete example just to clarify the lesson. So let's say our matrix is A equals 1, 2, minus 1, minus 1 over 2. Okay, so let's compute A inverse. This is going to be equal to 1 in the first entry, because that's the multiplicative inverse of 1, positive 1/2 in the second entry, minus 1 in the third entry, because that minus 1 times minus 1 is 1, and minus 2 in the final entry, because that multiplies with minus 1/2 to give you 1. How about A cubed? This is going to be 1, 8, because that's 2 cubed. Minus 1 cubed is minus 1, so that's there as well. Then minus 1 over 2 cubed is minus 1 over 8. Okay. If we wanted a to the minus third power, we would take the cube of the inverse matrix and get 1 over 8, minus 1, and minus 8. And as we've seen before, the inverse matrix to a cubed is the cube of the inverse matrix. And that's something we've seen before. Okay, so that covers diagonal matrices. And now we'll want to talk about a different kind of special matrix called an upper triangular matrix. And here we have the rule that Aij will be equal to 0 if I is strictly greater than j. Okay, well, where is that the case? So if we're on the diagonal, I is equal to j. So those are allowed to be non-zero. Okay. If I'm over here on this part of the matrix, that entry is the 1, 2 entry, so there j is bigger. So this stuff can also be non-zero. But then below the diagonal, I is greater than j, right? This is the 2, 1 entry, so we'll get a lot of zeros. Okay. You might also write this as just leaving out the zeros. Okay. Or you might write this as just one big 0. Okay, and an example might be, let's get this in a different color. Okay, this is an example of an upper triangular matrix. Obviously, there are some 0 entries above the diagonal. Okay, so 0 entries are allowed here. The only rule is that below the diagonal, all the entries have to be 0. To be here. These must be 0. Okay, and we're talking below the diagonal. Okay. So So let's think about what a product of two upper triangular matrices looks like, and we'll do an example here. Okay. And let's multiply that by this matrix. Okay, and what's the result that we get? So recall, we'll use the row-column multiplication rule to multiply these two matrices. First, we should observe that this is a 3 by 3 matrix. This is a 3 by 3 matrix. So the results we would expect to also be 3 by 3. Right, just taking the outside entry here, after confirming that these two match. Oops. Okay, so let's do it one entry at a time. So for the first entry, we have 3 times 1 plus 1 times 0, 4 times 0, so it's just 3. Then we have 3 times minus 1 for the 1, 2 entry. We take the first row, dot the second column, and we get 3 again. This is minus 3, actually. Then we multiply the first row by the third column, dot product, and we get 3 times 1 minus 1 times 1 plus 4 times 1, which gives us 6. Okay, then the next entry, we have 0 times 1 plus 1 times 0 plus 5 times 0, so that's 0. Then for second row, second column, we get 0 times minus 1 plus 1 times 0 plus 5 times 0 is 0 again. And 0 times 1 plus minus 1 plus 5 is 4. And for the third row dot the first column is 0, third row dot the second column is 0, and the third row dot the third column is 2. And so we'll note this is also upper triangular. And this is true in general. Whenever you multiply two upper triangular matrices, this will also be upper triangular. Okay? How can we tell if a given upper triangular matrix is invertible? Well, recall that for a diagonal matrix, the rule is that it's invertible if and only if the diagonal entries diagonal entries are all non-zero. The perhaps surprising result is the same is actually true for an upper triangular matrix. Okay. The same rule holds for upper triangular matrices. Specifically, an upper triangular matrix A is invertible if and only if all its diagonal entries are non-zero. Okay. So let's compute the inverse of an upper triangular matrix. Okay, so obviously all of the diagonal entries have to be non-zero. So let's do, and up here we can have Okay, so how do we compute an inverse? We augment by the identity matrix and do Gauss-Jordan elimination. As you can see, here the Gauss-Jordan elimination, you're always going to be adding rows up. This is why it's so important that these diagonal entries are invertible, are non-zero, because if they weren't non-zero, you wouldn't be able to get the leading ones that you need here. So let's start by multiplying column 1 by half, column 2 by, row 1 and row 2 by a seventh, and row 3 by minus, and we get 1, 4, 4, 1/2, 0, 0. Then 0, 1, 2/7, 0, 1/7, 0, and 0, 0, 1, 0, 0, minus 1. Okay, and at this point, we're going to add minus 4 times the second row to the first row. So we get 1, 0, and then minus 8/7 plus 4 is going to be positive 20 over 7. Okay, followed by 1/2 minus 4 over 7, 0. And then the second row, 0, 1, 2/7, 0, 1/7, 0, 0, 0, 1, 0, 0, minus 1. Because we don't have to cancel, this entry is already 0. Okay, so this is already 0, means that we never have to add one row to a row below it. That's why we never run the risk of getting in a non-upper triangular matrix in this process. Already 0. Let's grab this matrix. Okay. And that was a 4, so let's correct that, and here we go. What's left to do is just to get rid of the entries above the third leading one. So we can take minus 2/7 times row 3 and add it to row 2, and minus 20 over 7 times row 3, add that to row 1. Okay, and what we get is very simple. 1, 0, 0, 1/2 minus 4 over 7, and positive 20 over 7. Okay. 0, 1, 0, 0, 1/7, positive 2/7, and 0, 0, 1, 0, 0, minus 1. Okay. And this is our, let's use a different color. This is our inverse matrix, okay, which we got using Gauss-Jordan elimination. And as we predicted, this is upper triangular, because when we do this process to an upper triangular matrix, we only add the rows up. And so we're only going to run the risk of, first of all, we never swap rows. That's also important. And we also only add rows up. So we're only ever going to put non-zero entries in the upper triangle of the matrix. Okay, so lower triangular matrix, I'm just going to do a brief slide of this because it's basically the same as upper triangular matrix, except you have Aij is 0 if I is less than j, strictly less. So on the diagonal, it's allowed to be non-zero, and below the diagonal, it's allowed to be non-zero. Okay, so that looks like non-zero entries here on the diagonal, as well you have the non-zero entries here, but everything up here is 0. Okay. This is an example of a lower triangular matrix. And we can include a concrete example as well. 1, 2, 5, 4, 0, minus 3. Okay, this would be an example of a lower triangular matrix. And the analogs of the same facts for upper triangular matrices are true for lower triangular matrices. For example, the product of lower triangular matrices is lower triangular. If you take two lower triangular matrices, you multiply them, the result is lower triangular. A lower triangular matrix is invertible if and only if all diagonal entries are non-zero. The inverse of an invertible lower triangular matrix is also lower triangular, just as the inverse of an upper triangular matrix was upper triangular. Okay, let's just take note of an operation we haven't addressed yet. Recall that transpose of a matrix is when you reflect it across the main diagonal. So A transpose, when you look at the ijth entry of that, that's equal to the jith entry of the original matrix A. So recall, so if A is equal to 1, 3, 5, 7, 0, 2, minus 1, minus 2, minus 3. Okay, just an example of a matrix. Let's get this in green. Okay, then A transpose, you reflect across the diagonal. So the diagonal entries actually stay the same, but then everything else reflects across. So, oops, this should be 2 minus 1 minus 3, and this should be 7, 0, minus 2. Okay? So we can make the observation that if A is diagonal, after you reflect across the diagonal, it's still diagonal. So A transpose will also be diagonal. Okay, if A is upper triangular, let's think about what happens when you do the reflection across the main diagonal. Everything above goes below. So similarly, everything below goes above. Since all of the entries below the diagonal are 0, that means everything above the diagonal now is 0 in A transpose. So that means that A transpose is lower triangular. Okay, and similarly, if A is lower triangular, after you reflect across the diagonal, we find that A transpose is upper triangular. Okay. Now that we're addressing transpose, we're interested in matrices that satisfy the following nice property. When is A transpose equal to A? Okay, so that taking the transpose actually doesn't do anything. Well, first of all, we know that A has to be a square matrix, because the sizes of the matrix, if A is m by n, A transpose is n by m. So you switch the order of the dimensions. So if A is m by n, that means A transpose is n by m. So that means that m must be equal to n, if these two are equal. Okay. Now, what's the rule for the transpose? The ijth entry is going to be the jith entry of A. But if A transpose is equal to A, that means that Aij is equal to Abi. So in other words, the the entry in the ith row jth column has to be the same as its reflection across the diagonal to the jth row ith column. Okay, so let's look at a couple examples. So if we have this beginning of a matrix, let's fill one more entry in. In order for this to be symmetric, I need the reflection across the diagonal to also be the same as what we start with. So this has to be 2, this has to be 3, and this has to be 6. Now, when we take the transpose, the matrix stays the same, because swapping the opposite sides of the diagonal doesn't change anything. Okay, so that's an example. A non-example would be a matrix like 0, 0, 0, 1, 1, 0, 0, 0. Even though this matrix looks very pretty, when you swap rows and columns, you'll see that this actually has a different image, right? If this is our A, let's make this a bit smaller. So if this is our A, then A transpose would be 0, 1, 0, 0, 1. And our 1 entries would be in different places than they started out as. So that's why these are not, this is not an example of a symmetric matrix. Okay? Even though it's quite nice. Okay, so what preserves symmetry? Obviously, transposing preserves symmetry because if I take A transpose, if I know that A transpose equals A, then certainly the transpose of A transpose also equals itself, because they're both equal to A. Okay, so you can take the transpose of a symmetric matrix, still symmetric. How about addition and subtraction? Suppose A and B are symmetric. Then A plus B, well, the transpose of that, by properties of transpose, is going to be equal to A transpose plus B transpose. But that's going to be the same as A plus B, because both A and B are symmetric. So that means that A plus B, since its transpose is equal to itself, that must mean A plus B is symmetric. How about A minus B? Same idea. If you apply the transpose, it distributes over the subtraction, and then you apply symmetry of both to find that it's equal to A minus B again, so A minus B is also symmetric. How about scalar multiplication? So if A is a symmetric matrix, then Ka, what happens when we take the transpose of that? Well, since the K multiplies everything in the matrix, this is the same as just K times A transpose. But we know that's going to be equal to Ka because A is symmetric. So that means that Ka is also symmetric. K is a scalar. Okay. How about a product of symmetric matrices? Well, these two, you can check, are symmetric matrices, right? This is equal to that, and this is equal to that, and the diagonal entries don't affect anything, so these are perfectly symmetric. So both symmetric. And what happens when we take the product? So that's going to be equal to 1 times minus 4 plus 2 times 1. Then 1 times 1 plus 2 times 0, 2 times minus 4 plus 3 times 1, 2 times 1 plus 3 times 0, and we obtain minus 4 plus 2 is minus 2, 1 plus 0 is 1, minus 8 plus 3 is minus 5, and 2 plus 0 is 2. So these two entries are obviously not the same, not equal, so the product of these matrices is not symmetric. So this is an example of a matrix operation which you can plug symmetric matrices into, but you'll get out matrices that are not symmetric. Okay. On the other hand, there are some products that will be symmetric. So if you take any matrix A and you multiply it by A transpose, this will be symmetric. And similarly, A transpose times A. We can see this to be the case if we consider the transpose of A times A transpose. Okay, whenever we take the transpose of a product, that's equal to the product of transposes in opposite order. Okay, so this is A transpose transpose times A transpose. But this is equal to, we know that transposing twice gives you what you started with. So this is equal to A transpose. And that tells us that this is symmetric, because if you are equal to your transpose, you're symmetric. Similarly, A transpose gives us A transpose times A transpose transpose. Again, that means that we have A transpose A here, which is what we started with. So this is also symmetric. Okay, and we can, and this is true even if A is not a square matrix. True for any A. Okay, so let's see an example of this. So if we have A equals 1, 3, minus 2, 4, 0, 5. Okay, we can check what A transpose looks like. So A transpose is equal to 1, 3, minus 2, 4, 0, 5 times 1, 3, minus 2, 4, 0, 5. Note that you're never going to run into problems with the sizes of the matrices, because when you take the transpose, the first coordinate of the matrix, the second coordinate of the matrix itself is equal to the first coordinate of the transpose. So the multiplication is well defined. And we get 1, 3, minus 2 dot 1, 3, minus 2, which gives us 1 plus 9 plus 4, or 14. Then 1, 3, minus 2 dot 4, 0, 5 gives us 4 minus 10, or minus 6. 4, 0, 5 dot 1, 3, minus 2 is minus 6 again, and 4, 0, 5 dot 4, 0, 5 is 16 plus 25, or 41. The fact that these two are reflections of each other is 100% coincidence. Okay, and A transpose A. We have 1, 4, 3, 0, minus 2, 5, and 1, 3, minus 2, 4, 0, 5. And note we're going to get a different size matrix. The first one was 2 by 2. This one is going to be 3 by 3. And first entry is 14.14, or 17. Second entry, that's 1, 2, gives us 14.30, or 3. Then 14 dot minus 2, 5 is minus 2 plus 20, or 18. Okay, second row, first column is 30.14, or 3. 30.30 gives us 9. 30 dot minus 25 gives us minus 6. Minus 25.14 gives us 18. Minus 25.30 gives us minus 6. Minus 25 dot minus 25 gives us 4 plus 25, or 29. Okay, so here again, you see that the entries below the diagonal match the entries above the diagonal, and that's because the products, the dot products of the vectors that you're taking, it's the same set of dot products, just in a different order, right? The third row dot first column is the same thing as the first row dot the third column. Okay? And that's why we end up getting the same thing above and below the diagonal. And with that, I thank you for attention, and I'll see you next time.